You guys ready? Oh. I guess I'm not ready. Do I have to have it remote? Well, that's from the Game Jam this weekend, so let's see. Digital Zoom. Video?
Yeah.
No?
It's going to probably spend 30 hours.
And there it is. Thank you. I can computer. Okay. Game Jam, how was it? Yeah.
Draining.
Draining, yes. How many folks participated? And was it as horrific as you thought that it might be? Yeah. Yeah, probably. Good. And then anybody win in here? One of the 5 teams? Very good. So internship possibilities? Possibly, yes. Okay. Which team was yours? Okay. I thought prevention was cool. I also liked, they had one called Egg Defender. I don't know if you can imagine what it is, but you had all these little swimming creatures that were, okay. But it was pretty cool. All right, so I guess you're here because we were supposed to review, and so that's what we need to do. What do you suppose is going to be on the midterm?
Everything.
Just about everything. So what are the major things that are really important? Should you have read the book? Yes. And so maybe just to be nasty and make sure you've actually done that, I'll pull some major concept from the book. You bought that book for a reason, and you should learn everything you possibly can from that book. Trust me, it's going to pay off. There's some wonderful stuff in there. I know a lot of you don't like to read, but that's just what college is about, right? Could you pull that door too, please? Either one of you. Well, you had a laptop. See, this other guy just... I'm just messing with you. Okay, so the first things that we talked about, the main loop game elements, all these kinds of things, this is really good to know, especially when you start diving into other technology. You get into Unity, you get into UDK, any of these things, you're going to see commonality that cuts across all of these game engines. And so what are the major things? If you dive into the Jeff 3D engine, what should you expect to see? Okay, so in terms of these callback functions, I don't know if I wanted to hear what you just said. But yeah, you should expect to see that you get these callback functions. What are callback functions? Functions that run constantly or at the beginning or at the end, something like that, but they get called when events occur. Okay, so this is not like what we've seen in the past where you have main and you start at the top of main and then you finish down to the end of main. That's not how these things work. What happens, you have a loop that's running usually behind the scenes, and then as events occur, it calls update, it calls draw, it calls initialize, it calls all of these things that you probably have seen in XNA or whatever it is that you're working in. Yes? Okay, so that's the major concept. I don't want to dive too far into that. 3.2, section 3.2 was something out of the book. You should probably recognize a majority of this, and I think this was the language comparison kind of chapter. You probably recognize object-oriented programming. What are some of the trade-offs here in languages? C++ is definitely the best, right? You guys have all taken data structures probably to get into this class, or most of you have. I see some people shaking their head no. Just be prepared if you have not gone in data structures yet. Has anybody successfully survived? I think we should pass out T-shirts when you get through data structures. What do you think of that?
Well, it wasn't hard for us because you went over it.
Data structures, I hate to say should be that bad. You need to have a total mastery of everything from 1301, 1302, and data structures. I hate to say the rest of it is kind of icing, but it is. You get into specific kinds of things. But as a programmer, that's the core of what we do. Okay, so what are the pluses and the minuses of C++? I'm not going to do that. I think everybody kind of understands that. Java, it has its benefits. Scripting languages, if you have not yet picked up a scripting language, what language should you pick up?
JavaScript.
Okay, those are the two that I would recommend also. So Lua is good for what? Game stuff, yeah, okay. And then JavaScript is good for what?
Android.
Everything else. Okay, so if you're a really good JavaScript programmer, chances are that you will have a job because everything that's web deployed, all these things, all these scripts are typically done in something like that. PHP and Perl are really good things to know also. Okay, yeah, Python. I'm not a real big Python fan, but I know that it's popular, if anything. Okay, so review that on your own time. I'm not going to waste any more time. Here's the recorded lecture if you've missed it. Game design documents. Why do we need them?
So that we know what we're doing, organization. And most
Has anybody accidentally coded down the wrong to get money? That is an excellent point. We'll come back to that one. Has anybody coded down the wrong path before? You're like, hey, I'm just going to start coding, and then what happens?
I can throw away all this.
You might as well trash it. You just wasted all of that time. And software engineering kicks in here big time, not only from the requirements and specification and all that kind of stuff, but what happens if I find a bug in the requirements of this project that I'm working on?
Easy to change.
It's easy to change. How long does it take me to change? Boom. What happens if I find it in the implementation?
Takes a while.
What happens if I find it in the maintenance?
Goes to shop.
They say that every phase that you go through, it takes 10 times more time and money to fix that bug. Okay, so it's important to do these things early. And so we have those benefits that you've seen from software engineering. What are the 4 major design documents or documents that we've seen in this class that we talked about? Well, be careful when you say game design doc, because we didn't talk about a game design doc necessarily. What's that?
A pitch.
Not the MDA. That's a game theory. The pitch. What do we call that? It's not pitch. The concept doc. You wrote one. Yes. Okay. What's the other? What's the second thing? Nope. Not design doc. You could just call it the money document, right? Okay, what do we call that for real? That's the game proposal, right? And so you need to know what's involved in all of these things. I'll let you do the research on that, but that's the second one. What's the third one? The functional spec, and what's the fourth one? The tech spec. What's the difference between those two? Functional is what it does, and the tech spec is how. And you're going to see that again as a software engineering concept. That's pretty common. Yes? No, I cannot. Somebody else can.
Yeah, you said concept.
Concept?
Money doc.
No, don't call it the money doc.
You
You could call it. Game proposal. Game proposal? I'm not repeating them. Somebody else can. You need to know those. You need to know what's in them, right? Okay. What else? Did you guys ever see this? Some of you have probably seen this. Here's an example of a game called Race and Chase. This looks awesome, doesn't it?
Oh yeah. I want to buy GTA.
Here it is. Look at all this stuff, man. That is sweet. Target system. It runs on DOS, Windows 95. Here's the concept. The aim of Race and Chase is to produce a fun, addictive, and fast multiplayer car racing and crashing game which uses a novel graphics method. Would you invest in that?
No.
Race and Chase, probably not. What is it? Grand Theft Auto. This is the design doc for Grand Theft Auto. If you're interested, check it out. I think they made some money off of that, too.
It's now
Just
kind of a popular.
Yeah, it might have been popular. Okay, pitches in class, we've done 2D sprite animations, we talked about this. What do we know about sprites, animation, animated sprites? What do we know about that? You got a sprite sheet. You guys have all coded that stuff up. You're cool with it, right? So we know about how those things work. If you want to see one, there's one. Don't confuse an animated sprite sheet with an actual just sprite sheet. Here you can see we can have a sprite sheet that you could do animation from. The animated sprite sheet, well, of course, was just for one character, and then we did all that trickery there to make the animated sprite. Yes? Any questions about that? Hearing none. Fairly straightforward. Okay, 3.3, we talked about different kinds of data structures that you might use in a game. So what's the difference between an arrays and a linked list and all that kind of stuff? I think everybody knows that. What's a dictionary?
It's an array with a map with a set of keys.
It's a map with a set of keys. A dictionary and a map are basically the same thing. Okay? So how does this thing work? What I do is I take an identification piece of data, some kind of unique ID, and I can use that a couple of different ways, but then it directs me to where inside the array I can find the rest of the information that I'm looking for. Give me an example of that. It might be your social security number. I could take that. I could do any number of things, and then it would tell me where to find the data. If you haven't played around with these, take 5 minutes out, go to Wikipedia, check them out, and then code something up, and you'll feel better about yourself. You should be doing this all the time. Every day you should be programming. Nobody's making eye contact, or some people are making eye contact. Okay, other things that you've probably seen, stacks, queues. I'm not going to get into that. We talked about bit packing. What is bit packing? Well, it's not just network programming, but what are you doing with it? It's used often in that.
You're
Yes.
sending data as bits.
You're saving data as bits, yes? Don't we always save data as bits?
Well,
Each bit represents.
I want to point something out about that answer. Is he right? Can I give him credit for that answer?
no.
Half. The reason that I'm bringing this up is because what he said is technically correct, but he didn't state it the way that I'm looking for as a grader. Think about if you're, during the exam, you write it as if you're trying to explain it to another programmer or somebody who doesn't understand that concept, okay? So you can assume that I have a base knowledge of those things, but more specifically, what would you say bit packing is?
It's like assigning specific things to.
What are we specifically talking about? Yes.
You're basically using a string of bits as bool values.
Yes.
That will be fed into questions.
Game state, right? We're talking how we can save game state as a series of bits. Why is that such a big deal? How many possibilities are there in most games? Did you pick this item up? Did you talk with this person? Did you do this quest? All those kinds of things. There's no reason to take up 64 bits to say, yes, this person did that. That would be insane, right? So you try to make all these things as slick as possible, and a lot of times you have constants and things at the top. We had talked about bitwise and bitwise OR. You guys have seen these. These are different than the things that you probably have worked with before. You should know how to count in binary. Anybody that attends this university should count in binary. Okay? So let's just do this. What number is that? 10. How do I know it's 10? Because it says 1010, right? It's 2 tens, right? So maybe it's 20. Okay, how do we do this? This is 2 to the 0, 2 to the 1, 2 squared, 2 cubed. Right? So I can just add all of this stuff together. If you want to look at it like this, 0 times this is 0. 1 times 2 to the 1 is... You sure? 0 times... Okay, and 1 times 2 cubed? What do we have summed up total?
8,000.
Okay, now what if I said 8,000? Okay, virtual slap there, okay? I'm not promoting violence, by the way. Right, so what if I said that this was a signed number?
It could be odd.
Negative. No.
I have not heard the correct answer yet. What do I do? First of all, what do I do?
Take the left.
Let's take a step back. What's the difference between signed and unsigned? What does that even mean? Signed means that it has a sign. It has a positive or negative sign associated with it, right? So we can get into negative numbers here. Unsigned means it's greater than 0. 0 or greater than 0, right? Okay? What's that? Yeah, and so you expand the range. In fact, we can test that, right? So what if this were a signed number, meaning that it has the possibility of being a negative number? The leftmost bit, this guy right here, is negative. You with me? So what does that mean? It is a negative 8 plus 2 gives us negative 6. I'm not going to talk about anyone else. I'm being recorded right now, so I can't do it. Okay? Let's talk about the min and max kind of thing, and maybe this will, if you haven't seen this trick before, it's actually pretty cool. What is the smallest number I can represent with 4 bits? Assuming that we have a signed system. What's the smallest number if I have 4 bits that I can represent? What is that going to look like? 1, 0, 0, 0. Why? Because this 1 right there is negative 8 plus 0 gives me what? Negative 8. So what's the largest number I can represent with 4? 0. I don't want this thing to be a 1. And then what? 1, 1, 1. So everything over here is going to be positive, and this would be a 0. So what is that going to give me?
7.
That's going to give me 7. See how it's off by 1 just a little bit? Let's talk about Super Mario Brothers. Was anybody the Super Mario Brothers king? It was me. I could save the princess in 7.5 minutes, and I'm not 7 minutes and 19 seconds to be specific was my record. Okay, I played a lot of this. I learned how to get this turtle falling down the stairs. Anybody know that trick?
Yes.
Get the turtle coming down the stairs. You could jump on the turtle, and all of a sudden it would lock in, and you could just go. It would just keep going and going, and you get 99 lives, and then you get the next live, which is what? I know what you're saying. Hey, maybe it could overflow or something. That's not where I'm going. It could not represent that number, so it picked cloud. And then it picked turtle. And then it picked some weird part of Mario. And then it picked, and you start seeing all these weird symbols pop up there. But what it was trying to say is, hey, you have a maximum number of coins. You have a maximum number of lives. It was an 8-bit Nintendo, yes? What's the largest number I can represent unsigned, because you can't have negative lives, unsigned with an 8-bit system? What would it look like? No,
255.
One, right? What does this turn out to be if you did the math?
255.
255. You ever notice everything capped out at 255 in the old 8-bit Nintendos? It's because of that. Right? Wax on. Wax on. Does that make sense? Now, what number would this be if it were a signed system? It would be negative 128 plus all of this mess, which is 127, gives me negative 1. You need to know these things. Employers love to ask questions like this. I would not ask a question that said, hey, if I wanted you to express this in hexadecimal or octal, what's the trick there? This is not going to be on the exam. I'll go ahead and tell you, but you need to know this, right? If I wanted to say, how do I say this in octal, and I'll throw in some zeros here just for kicks, what is that in octal? Split it up in what? In threes. Here's a 3. What is that? Oddly enough, it's 3. Okay. What about that? 7. What about this? Uh-oh. What do I do?
Add a 0.
Add a 0, and it's 273 in octal, base 8. Cool, huh? What if I said to represent this in hexadecimal? What would we have? Group it in 4s. What number is that? B. Who said that? Very good. All right. B. Why is it B? Because it's the number 11. What do we do when we have a 10? It's A. B is 11. What about this guy right here? Oh, crap. Okay. BB is in hexadecimal. So you see, bits are important to computer scientists. All right. Multiple inheritance. Why don't we allow multiple inheritance? Wolfman. What's the diamond of death, right? What's the problem with the Wolfman? I'm not going to ask it like that, guys, but what's the problem with the Wolfman example that we had? What does he inherit from? Absolutely, right? Because we could have walk or eat or any of these things. They could be, transcend down here into wolf and man. And then when you have this inheritance from 2 things, which one do you inherit, right? Which one is the overriding thing? Welcome to the standing classroom. It's a new concept. We're trying. I'm just kidding. Okay. And then the last thing I think we talked about, there's limitations to inheritance. You can read that on your own. What is component system organization? Oh, there's a seat right over here, too, if you want. Yeah, I think we've thinned out just a little bit, but not too much. And hopefully the midterm will not thin the class out anymore. I'm not implying that. What is component system organization? It is not the opposite of a class hierarchy, but it helps to overcome some things. What are we doing? Think unity when you think this. You're adding stuff to it. So the example that they had in the book here was that you had this game entity that had, that it was a talking sword, I think. And so if you wanted to make a talking sword, you bring the sword to life, and then you start adding different components to it, right? Like a new damage component. If you wanted to be able to see it, you could have a rendering component, a talking component, a collision component. All of these kinds of things you could add to an object. And it overcomes all of these awkward situations where we have multiple inheritance. Yes?
So it's basically just really, really modular.
Yeah, you can just think of, you've got this base object, and you've got all these little components dangling off of it, right? And you're just constantly adding more functionality to it. XML files.
Okay. Is that component?
Yeah. Why are XML files? I'm not going to even say just XML files. Why would you want to use external text-based files?
It's easy for someone to read.
It's easy for somebody else to mod, right? So if you wanted to have a level design or something like that, that's why you would have these external kinds of things. If you haven't done that in your game, it will actually save you a lot of time. You're going to take the hit initially, but then it's going to pay off in the end. And then I'm not going to ask the design patterns. There's no way. That's a software engineering concept. Okay, any questions up to this point? Hearing none. Moving on. Mathematics of gaming. What are we talking about here? Matrices and? Yeah, a little bit of trig. Not terribly. I mean, everybody should have passed trig. And if not, don't be ashamed. I won't call you out. Slideshow from, current slide. Okay, we'll get into trig. I'm not going to ask you a lot of trig questions. I'm just assuming that you know that. Converting radians to degrees and degrees to radians. You should know this off the top of your head. What's the easiest way to remember this? You know you have pi and you have 180, right? Those are related.
Try one if it doesn't look right.
Okay, I'll accept that answer. Just remember, huh?
Whatever you want to go to.
The one you want to go to is on top, right? So if you want to go to radians, what should be on top? Pi over 180, and the opposite would be 180 over pi. So that's the easiest way to convert. Okay. Other things, I've got to skip over all that stuff. We're not going to finish if we don't. Don't beat yourself up here on knowing things like the sine of alpha is the square root of 1 minus the cosine squared. I mean, I'm not. Out of all the gaming that I've done, I have not used that at all. Okay, inverse trig. This is important. What are we talking about inverse trig? Arc, sine, arc, cosine, these kinds of things, because you know that later on when we start talking about vectors, that's going to be really important. That's how we're going to undo the trigonometry there. So keep that in mind. If I want to know the angle between me and an enemy, what do we do?
Distance.
There's a difference in our x and a difference in our y. Yes? Okay, so this works across multiple dimensions also. So what we could do is we could look at it as the difference in x and the difference in y, and then we could pass that off to what function? Our friend? Yeah, atan 2. That's one of the best functions that you're going to be using. It's very common. It's a really good one. Okay, 3D stuff you probably know. If we have a model that's there, it's comprised of a whole bunch of points, and those points are then assembled into triangles. You guys remember this from the graphics lecture, hopefully. Okay, so we call those things vertices, right? A vertex or vertices. We have triangles. Why do we have triangles?
I forget what it's called, but it's light when you turn it, which is normal.
It's easy to find the normal. There's all sorts of benefits, but graphics cards are actually now, they only accept triangles, right? They're very good at processing triangular kinds of things. And there's also, if we had a square, remember what you could do is you could twist the square, and what would the normal look like? First of all, what's the normal again? It's perpendicular to the plane that you're talking about, right? So if we had a square, what's the problem with that? If I twisted these things, let's say in these arbitrary ways, what would the normal look like? Who knows, right? So it causes all sorts of problems. Okay, here we get into vectors. Realize that vectors can be interpreted a couple different ways. You could say that a vector is a point. It would still suffice. But most of the time we use it as a direction and a magnitude, right? So it's going this way and it has this much strength behind it. We can do a row or a column representation. And they typically, if you want to see something cool and play around with this, just draw a little arrow. Maybe I'll put +1. If I see a little arrow up above and say, hey. Also, before I forget, yes, if you draw something on the midterm exam, I don't care what it is, you get +1. Please don't make it like X-rated, you know. Right. Oh, it's too late. Yeah. Okay, moving on. When we add two vectors together, how do we do that? We can do it visually like you see here, or we could do what? If I told you add these two vectors together, and I don't know if I would do that because it is just too simple, what would you do? It's all component-based, right? So we take the first component, and then we add them together, and then we take the second component. So, for example, 135 plus 10, 4, negative 3 gives us 11, 7, 2. I think everybody sees that we just added those components together. Okay? We can do subtraction the same way. We can also multiply a vector by a scalar. What's a scalar? It's a constant number, right? And realize that a scalar could be something like 3.4. It doesn't have to just be an integer. So if I were to multiply 6 times 135, what would I get? 6, 18, 30. So you can see it just basically, what is that called? Commutative? You could think of it kind of as distributive? Something like that, yeah. It's one of those laws that we've seen several times. Yeah, so we can't multiply two vectors together, but we do have two different operations. We have cross product and DOS product. We could say DOS product. That would be incorrect. Cross product and dot product, and we'll talk about those in just a second. We have to talk about normalization and magnitude and things like that first. So things that you should know how to do. The magnitude is denoted by these two railroad tracks here on the side. So if I asked you to calculate the magnitude of vector 1, 3, 5, what would you do?
Square one and square.
It's basically the distance formula, right? So here, 1, 3, 5, we would take 1 squared plus 3 squared plus 5 squared, take the square root of that, and that gives us a magnitude of square root of 35. If I give you a question like this, it is okay to leave it as an expression. I don't want to see approximately 5.91, any of that kind of stuff. That's not what I care about. I care that you understand the concept here. Does everybody get that? There is no need to bring a calculator. You will not use a calculator on this exam. Pencil and paper only. Okay? If I told you to normalize this vector, what would you do? What does that even mean to normalize the vector?
Give it a length of 1.
You want to shrink that down or expand it out so that it has a length of 1. So how do you do that? Divide each component by its magnitude. So that's a pretty straightforward thing. So remember, it's a two-step process in that case if I ask you to normalize the vector. Are there any questions about that? Do I want to invite people?
Yes.
Who could I invite?
Who even uses this? We could invite Jessica.
No, okay, moving on. What? People were offended by that. The dot product. This is important because it's the basis of a lot of lighting calculations that we use in graphics. So everything that you see that's lit, for the most part, uses this equation right here. The dot product is basically the way that we determine the angle between these two vectors, right? So it's a very useful kind of thing. It's denoted just with this dot operator like you see here. This, again, is a component-wise operation, and you could think of this as multiplication. The reason I say that is because if we have these vectors 1, 2, 4 and 8, 1, negative 2, component-wise, we're going to go through there and create something that we're going to sum up. So it's going to be 1 times 8 plus 2 times 1 plus 4 times negative 2 gives us 2. Realize that in this example, this is not a normalized example, right? We have 1, 2, 4, not normalized clearly. Has to be longer than a unit vector. So this 2 right now in this form is meaningless. However, if we do all of this kind of stuff and they're normalized, it's going to give us the what? The cosine of the angle between those vectors. I want to say that again because a lot of people they're going to write down it gives us the angle between this. It's not what the dot product does. It gives us the cosine of the angle between those things. So what is the possible range if we have two vectors? What's the possible range of values we could get from the dot product?
Negative 1 and 1.
Negative 1 to positive 1. Why? Because that's the only thing we can take the arc cosine of. You with me? This is the boring math section. Hang in there. You can do it. All right. So let's see an example here. If I ask you, hey, we have these two vectors right here. Are they normalized? And I'll come back in just a second. Yeah, they're normalized. How do I know that? Because it is of length 1, right? So what's the angle here? It's 90 degrees. I think everybody can see that. So if we were to take the dot product, it's going to be 1 times 0 plus 0 times 1 plus 0 times 0 clearly comes out to be 0. Is that our degree? No, it's not. So what do? Take the arc cosine of it, and what do we get? That's going to come out to be 90 degrees. Yes? You had a question?
Yeah, is the exam going to be heavy on the math aspect?
There will be math. It will not be heavy on math. I would say 1 or 2 out of 6. I don't know, something like that. You need to know this. There's no doubt. And if you're not going to learn it here, where are you going to learn it?
The internet.
The internet. Maybe linear algebra. Maybe you'll never learn it. I don't know. And again, what are the two things? The reason I'm bringing this up because I really truly believe it's important. What are the two things gamers have to know?
Math and programming.
Be a master of C++ and 3D math. And it says I'll pull up job ad after job ad after job ad, and it says C++ in linear algebra is essentially what you need to know. Okay? You have been warned. All right, so I'll let you go through the other examples. I'm not going to waste time. I am not going to ask you about projection. Don't care. All right? Cross product is important. Why is the cross product important to us? What does it give us? Yeah, it's to give us a normal, but what is the normal? It's going to be perpendicular to these two vectors. So here you can see I have vector C and vector A, and what's going to happen, or do I have vector A and B? It doesn't really matter.
A and B.
Yeah, okay, so I have A and B, and it's going to give us this third vector that's perpendicular to the two. Why is this so important? Because if I'm trying to determine the normal of a plane or normal of a triangle, what do I have to do? Take the dot product between, the cross product between what? Vector, the first vector and the second vector, right? Well, how do I get those? Magic. Elfin magic. Okay, use the points in the triangle. What do we mean by that? If I had point 1, point 2, point 3, or point 0, we'll do it that way, through point 2, realize that I can construct vectors between these. What does that mean? What's the vector here between P0 and P1? It's a component-wise kind of thing. So if I wanted this new vector between P0 and P1, I don't see X, Y, and Z here, right? Oh, well, let's just write them in. X, Y, Z. Okay, so then what am I going to do? The new thing, P, let's just call it P prime, something like that, because we all like that. What would I do? P prime of X, you probably saw this in your Bezier stuff, is going to be what? P0 of X minus P1 of X. So you can construct your own vectors out of a triangle. And you'll be the life of the party. Hey, do that trick again. I'll get out some paper. That will not happen. That will not
Well, it
happen.
depends on what kind of party.
No. It will not happen.
No math parties, no crazy wild math parties.
No. No, I'm we're done with that. Okay.
People dressed up as
So how do you actually calculate that once you know the two vectors from this triangle? What are we going to do? If I say A cross B, you can see that there's this formula that goes on. It's best if you were to visualize this and actually write it down like you see it here. Okay, so if I want to figure out the new X component, what is it? We have a cross here between AYBZ and AZBY. So you see why they call it the cross product? It's actually in the way that you calculate it. Okay? The next component over here, if we were to look at the Z component, which is the same thing as K in this case, then it would be what? So the cross here, AXBY, AYBX. And then what do we do for the middle one? I think you can figure it out. There's a pattern here. If you're good at patterns, there you go. All right. Matrices. Any questions about vectors before we move to matrices? Okay, what is a matrix? It's a 2D array. That's the way that programmers think of it, and it just stores a whole bunch of numbers. Realize that you can store all sorts of stuff about an object in a matrix. What can you store? Stuff.
position, rotation.
Position, rotation, scale, skew, all of that kind of stuff, right? All in 16 digits. It's not that we have to keep separate things. We don't have to have a separate translation matrix and a separate rotation matrix. It all fits in 16 digits, and that's why we like to use these things. Okay, we're going to break that rule a little bit later on when we talk about character animation, but pay attention, right? So here we go. Here's an identity matrix. What's the importance of the identity matrix? You multiply anything, we'll just leave it as anything, times this identity matrix, what do you get back? That same thing. Same thing as multiplying by 1, okay? Don't worry about determinants or transpose. I don't care. You should probably memorize these things. I don't think I'm going to require you on the exam to memorize these, but you need to know them. If I want to rotate a point about the x-axis, first of all, what does that look like? I'm rotating about the x-axis. That's, I hate to do this exercise with you, but you need to be, yes, it's this way, right? So it's your up-down kind of thing if you're writing a flight simulator. What about the y? That's going around, so this is your, what, rudder, I suppose? And then what about the z? What do we call those things on the side of planes? What? No, not propellers, no. Wings, but what makes you go like this? Ailerons, who said that? Very good. Yeah, flaps? What do flaps do? I think the flaps slow you down, right? We've gotten off topic. Let's move on. Okay, so you should know these. Realize there is a pattern associated with these too. You can see that cosine is always here in this upper left. If you were to look at the cosine and the sine that's there, that's always there. And also in the lower right of this kind of thing. Also realize that because this is the x, you can see that this is a 1 in the upper left. Right, so there's your x, there's your y, and there's your z. If you did the math, you would see how that works out. I would practice this just 1 or 2 times, do a real simple like 90 degrees or something like that, and see. Those are easy to test, okay? Now, by practicing, I'm sorry. Yes?
Since we are working 2 dimensions, x, y, and z, so why do we need column?
That's a great question. He says, why do we need a 4th column if we're only working with x, y, and z? Because in graphics, we have perspective division. I'm not going to say anything past that. Just say, okay, Jeff, that sounds good. Take a graphics class and you'll see where this comes into play. In the real world, could you get away with having just 3. Look at this. Couldn't we fit all of this in 3 and still get a rotation? Yeah, you could. But that 4th part right there is hyper important in computer graphics. That's why you always see a 4x4 matrix, and that's what the graphics cards support. Yes?
Isn't that done in part because it's a power of 2? Computers like power of 2?
Computers do like powers of 2, but it has to do with one of the final phases in computer graphics. And again, I'm not going to talk about it right now. We'll sit down a little bit later and just say, hey, let's drink some coffee and talk about... No, we won't do that. Okay, so let's see an example. If I were to ask you multiply this point by this matrix, what would you do? You'd freak out, and then what would you do? Okay, look at it this way. You have a left hand and a right hand. If we were going to, in fact, wait, let's visualize that. Here we go. Here's the first thing. First of all, understand what we're doing. You can see that the matrix is on the left side, right? Is everybody cool with that? The old point, or the point that we want to rotate, is the next thing in this equation. So what we're trying to do is to say, if I multiply this matrix here by this point, I should get a new point from that operation. Yes? Yes?
Yeah.
Okay. That's something, because when I say, if I were to throw this out there, half of you would foobar it. You would have things going all over the place. At least have the structure of what you expect to get in place, okay? So it's going to be matrix, old point should generate a new point. All right, so let's go through this right here. You can see that the row here of the matrix and the column of this point right here, we're going to multiply this component-wise. So it's going to be the cosine of 90 times 1 plus the negative sine of 90 times 0 plus 0 times 0 plus 0 times 1. Do you see where that came from? We've now calculated the new x position. Yes?
Yes.
Everybody see that pattern? Okay, so what are we going to do for the y position? We're going to drop the row down. We're going to do the exact same thing. So it's going to be sine of 90 times 1, cosine of 90 times 0, and so on. And you see that we get a 1. Same thing for the z.
You sum the result?
Yes, you sum the result together, yes. In fact, I did that down here at the bottom, so you can verify this. So look at what we've just done. We said that we're going to rotate this thing by 90 degrees around the z-axis. What's the z-axis again here? Your ailerons, right? So it's going this way. If I were to take 1, 0, 0, where is that? 1, 0, 0. So it's over to the right, and I rotate that 90 degrees about the z-axis.
No, it's just, it's a.
What should I get? What's my new point? 1, no?
Or 0, 1, 0.
1, 0, 0 goes up to 0, 1, 0. What did we get? 0, 1, 0. You see, it does work, I promise. Play around with it. Get a piece of paper and a pencil. We're moving on. Okay, translation. Translation matrix is very easy to remember because it's this last column right here. You can see that we have an identity matrix, and then we have the amount that we want to translate by appearing in this 4th column. Right, so if we did the same thing that you just saw, and we multiplied this old point by this matrix right here, it's going to give us a 10 plus x, a 5 plus y, negative 7 plus z. Why did we go through all this rigmarole when we could just do addition to begin with? Why are we even using matrices to begin with? Because computer likes them. Yep, that's absolutely why. So we try to get everything into this form. You need to know this one, I would say, from memory because it's so easy. Right? I'm sorry?
I don't understand how you pass, like, what about pass? Where do you even pass the array?
Don't worry about that yet.
Somewhere.
I did a computer, we did something 3D in class, yes? We did a dragon. No. We did a dragon rotating or something like that, right? Look at that example and you can see how it's passed. I don't want to bog down application versus theory right now. Okay? Look at the example it's posted, I think. Yes?
So the first matrix is what you're giving it, you want it to move this way.
Yeah, again, breaking it down so that you understand. Here is the matrix, what I want it to do. I want to translate by x, y, and z. Those can be any numbers, it doesn't really matter, but I want to move this old point, which is 10, 5, negative 7, by x, y, and z.
Okay.
And so if you do that same matrix multiplication, we're going to get 10 plus x, et cetera, et cetera. Yep. All right. The other easy one is scaling. Why is scaling so easy? It looks just like the identity matrix, except down this diagonal, we're going to put how much we want to scale by. So it doesn't have to be a uniform scaling. What do I mean by uniform scaling? all of them being the same. No, you can scale it more in the y direction than the x direction or something like that. So you can start to squish these things across different dimensions if you wanted to. Again, this is very easy, so I could multiply 2941 by xyz, and I'm going to get 2x. You can do the math and see how that works. Yes? Any questions? Moving on? All right. Don't worry about lines. Or you should worry about lines, but not on this exam. Don't worry about that. Planes, no, we'll skip that. Okay. I think that was it. Any questions about the math side of things? Are you still alive? Yeah. Let's see. Am I still warm? Here we go. Bezier curves. Do we want to talk about Bezier curves?
We need to know the formula by heart.
Do you need to know the formula by heart? No. I would say the basic concept in this class. I mean, you guys have done the assignment, and if you understood the assignment, I think you understand it. Because honestly, what's going to happen is you're not going to have that thing memorized. I don't have it memorized. I have it roughly memorized and kind of what it looks like. Yeah, you're not going to do that. So how do they generally work? You have these points. You have a starting point and an ending point, and then what do you have in between? 2 control points that are influencing this thing along its path through life, right? So there you go. All right, we get into audio. I think we had talked about that. Let's just blow through these slides real quick. What is sound? I'm not going to give you something this obscure. That's kind of like what is life. So don't study that. I think everybody understands that sound are these compressions of air, and then it's a certain number of times per second that we call hertz, right? So don't confuse pitch, which is the frequency, with volume. What's the difference there? Pitch is how, when you say high, what's the problem with saying high?
How coarsely under the sound waves are compressed.
Well, it's because both ways.
You could say that the volume is high too.
How shrill?
High pitched.
It's the frequency, right? So we get back to that thing, right? So it's, you can start talking about the peaks and all of these kinds of things, you know, the distance between peaks and all that mess. Just understand that volume is volume, right? Don't say high because that's a horrible description. Okay, humans here only between 20 hertz and 20 kilohertz. And no, we will not be talking about the Brown frequency. We're not doing that. Spatial sound, we have 5.1. Everybody's cool with that. 3D sound. Let's get into human side. In fact, let's just do not memorize this. I'm not asking, and this is not anatomy, any of that kind of stuff. What is the ear canal? Can you imagine an administrator coming in and looking at that question and thinking, what the heck are they teaching? Okay, this is pretty important, though. The equal loudness contour means what?
As you go from pitch.
I don't know if I would ask this question, but it is a really important thing because it does tie back into things like how MP3s work so well. What does this mean? It takes more power to hear low frequencies, right? You think about the amount of power to get all of those waves and everything else, and we don't respond well to them to begin with. So it takes a mass amount of power. That's why all these subwoofers have 5,000 watts and everything else, trying to push all of that stuff so that we can be responsive to it. And then we get up here, you know, and we have this little dip, and it comes down, and right here at 4 kilohertz, that's a frequency that almost everybody's sensitive to. It takes almost no power to drive that frequency. Okay? That's what this equal loudness contour means. Okay? Decibels are what? Decibels. They are, yeah, the way that we measure the volume of sound, right? And also in gaming, this volume usually ranges between 0 and 1. So you can say, hey, 0 is all the way off, and then 1 is all the way on. They are also logarithmic, so be careful there. Human perception, how do we hear stuff from the right and the left? The difference, how do we hear stuff up and down? Yeah, okay, everybody's doing this. Yeah, now everybody's looking at each other's ears like, man, Jeff has some really big ears. That's a weird looking guy. And I want you to seriously sit there and look, not now, look at a human ear and be disturbed because it is a weird thing. Okay, but yeah, you get it. The same thing with forward and backwards. Those frequencies are cut off, right? And that's what these things do is they pick up different kinds of frequencies. Okay, how do computers perceive sound? Great question. How do they do it? How do we record sound? I know it says ones and zeros, but how do we get something that is a real-world analog artifact into a computer that's a digital system?
By measuring how far.
Yes, we have a microphone, and this thing has a magnetic, something or other that's driving it forward and backwards, right? So as I'm talking, this thing is vibrating, and then the computer is sampling that. How fast? 44,000 times a second, whatever, doesn't really matter. So you have to understand that you've got a cone that's going in and out, and you've got a computer that's figuring out where the position of that cone is, however fast you want it to do that. That's how we record sound. How do we play sound back? We reverse the process. We take all of these things and then we move that speaker to where it needs to be. So a speaker and a microphone are generally the same thing. Okay? Computers have to approximate what they've heard and assign it a number. This is a very key concept right here. Right? We'll skip all of that stuff. You've probably seen it. If we have a low sampling rate is, and you might want to write this down, you'll get them confused. Sampling rate is the number of times per second that the computer listens to the sound it's recording. The number of times per second that the computer listens to the sound that it's recording, okay? So if we have a low sampling rate, what's going to happen? You can see that we've got this guy right here, this waveform, and then this is what we're going to record. Does this look like the original waveform? There's no way. So what do we want to do? We want to increase the sampling rate, right? The number of times per second that it's listening, and this is going to give us something that's at least a little bit better. Now, you can get some really bad stair-stepping, right, some of these kinds of things, but for the most part, it's still better, okay? Versus bits per sample. Now, what does this mean?
How accurate.
Yeah, everybody, you can't do this on the exam. I see everybody's going like this. Yes, I understand.
It's going to be how accurate. When you draw the
Don't draw it either. No, keep going. You were...
It's going to be how accurate the sample is. Like it's going to be this high or this high. Or this high.
Yeah, you can think of it as the precision of it, right? We have to make approximations. We don't have infinite precision when we do that measurement, right? So we're trying to figure out how far the cone is. It has to fall on a particular boundary, okay? So in this example right here, we have 2 bits per sample. There is no such thing. It's just for educational purposes. Okay, so we have 4 different levels of approximation. So in this case, you can see that we have these kind of big-time errors between these giant steps that we should have recorded in the wave, right? So we get this kind of stair-stepping thing, whereas if we have 3 bits, how many levels do we have? How many different possibilities with 3 bits, guys? 8 different possibilities, right? So now you can see that our stair-stepping has been minimized. The problem is this quantization error that you saw here before. That's a big fancy word for saying how much error there is in the system. When we have to push it up or push it down, that's what we're talking about, the amount that we would do that in an incorrect way. Does that make sense, or was that a horrible explanation? Right, so bits per sample is how accurately you're going to record the position of the cone versus sampling rate, which is what? How often you're going to do that. Okay? I think we had talked about this also. I'm not going to be nasty and ask you about signal-to-noise ratio. I think that's a little bit too much. This is an important concept, though. If in the real world you are recording something that has exceptionally high frequencies, in the 20,000 range, you have to double the frequency that you're trying to record. Okay, so if I'm trying to record a 20 kilohertz signal or something like that, I have to record it at my sampling rate at 40,000. It's called the Nyquist theorem. That's an important practical kind of thing. Okay? Anybody else see that?
Yeah, I saw it too.
Okay. I thought, did I just black out? So welcome back, Jeff. You've been out for 15 minutes. Okay, so when we record things, realize that rock is different than Mozart. Why is this such a big deal? We talked about NPR. Everybody turns on NPR, and what do you hear? It's quiet. And then what? And then it's really loud. So these drastic changes in volume are different than rock, which is what? It's constantly full force, right? For the most part. I know there's ballads and things like that. That's not what we're talking about. So when would I use a high bits per sample?
Mozart.
Why the Mozart? You are right, but the question is why?
There's a level of difference in range.
You don't want to stair-step.
The problem is when it gets really quiet. What does it have to do? It has to approximate either up or down. So if you don't have a lot of bits per sample and it's quiet, you hear this, you're going to get a whole lot of hits because it's having to push those samples either up or down. Versus rock, which is always kind of this giant waveform, it doesn't really matter. Okay? Okay, what about sampling rate? Can I ever get away with a low sampling rate? Yes. With things that don't have wide frequencies. Okay? Ideally, you would try to get, both of them way, way high, but what's the problem? It creates a really large file. Okay, capturing sound, skip over that. Compressed audio. You guys know the lossy, lossless. I'm not going to ask that anyway. ADSR, I'm not going to really talk about that. That's a little bit esoteric, I think. MIDI, how does MIDI work? It's representing sounds electronically, Jeff. That's what the slide says. Yeah, but how does it work? People are saying this is totally irrelevant. Today we have everything as MP3, right? No. Did anybody work with some Berkeley folks? Their stuff sounds awesome, right? It was probably MIDI. You guys are like, no, I've heard a full-blown orchestra. No, it was probably MIDI. Just trust me on that one. Okay? So this is a really important technology because this, believe it or not, when you hear all of these fantastic orchestras and all these epic themes and da-da-da, and you hear brass come in and all this kind of stuff, and it sounds like a real orchestra, chances are it's not. You know why? It's way, way cheaper. You can't afford to hire out the ASO. If you don't know what that is, I don't care. Right? You can't afford to do that. So MIDI is still used today to replicate everything that we hear. Now, how does it work? You have a keyboard. You have some kind of input device, and what does it do? Does it generate sound? No, it doesn't. What does it do? It generates signals. That's all that it does, on and off or velocity information, something like that. So the files are really small, right? Versus something like a digital file format, which MP3 or WAV or something like that. What's the problem with that? Larger file, but huh? Yeah, it is popular. Yeah, that's a benefit too. What's the difference between MIDI and an MP3? MP3 is copyrighted, yes. Yes, that is true. That is true.
Variety just records the giant thing as MIDI can use.
You're recording a real-world artifact. One thing that MIDI cannot do is record human voice, right? So if I wanted to sing the next, well, I'm not going to sing, but if I wanted to do something like that, I really can't replicate that with MIDI. Or I can't do it easily, right? It would be a real nightmare. Yes?
So if I understand this correctly, you're saying that music and games and for the most part MIDI files?
MIDI, so that's a great question. He said, if that's the case, are they all MIDI files? Excellent question. Are they?
No.
No.
The same with movies.
And the same with movies? No. So what are they doing there? What's this relationship between MIDI and MP3s? They record it as a MIDI file, right? So it's just these on and offs. It's like, hey, you know what? We need to turn on this brass instrument or brass section at this particular frequency, this particular volume, all that kind of stuff. Once they've done all of that stuff and they have all the ons and offs, they send it to some processor that's the sound module piece of it, right? In fact, let's jump ahead here real quick. Here's the grand scheme of things, right? I have this keyboard that sends all of this on and off velocity information. It goes to this recorder, this sequencer. And you can think of this as laying down tracks, like you lay down the drum track and then the guitar track and everything else. And then that goes to a sound module, which does what? This is the thing that has the full-blown orchestra in it. It has the brass section. It has the harp. It has pianos. It has all of that stuff. And then what do? Once the sequencer pushes all that information, then we actually hear sound. We push it out to the speakers. Okay? So the question then is, what do they use in games? Do you get MIDI files? No, you get MP3s and OGGs and all this kind of stuff. So what's the relationship there?
You can export it as an OGG.
When they create the music, they'll do it using MIDI. When you receive the music, did the Berkeley folks send you a MIDI file? No, what did they send you?
They said it's the WAV.
Okay, WAV, MP3, OGG, all of the common things. So they'll actually record it and push it out and save it as an MP3. But the process is what I want you to understand. Make sense? Questions about that? Hearing none, moving on. Okay, well there you go. There's your difference. Sampling, we had talked about that. No, we'll skip over that. Sine, square, saw, no, that's just cool. Cool old school stuff. Interactive music, I don't know if I'm going to ask this, but it is important that you understand it. Typically you have a sound designer that does what? Don't say design sound. Sound designer does what, for real?
Decide what sounds good.
They have these huge libraries of all these different sounds, and they design the environment that you're going to be in. It's not a composer. It's not that they actually make music. Okay, so what do? They build stuff like this. They're very graphical in nature, right? So we have this application. This is Fmod right here. They'll create a theme. They'll drag it in there, and they'll figure out, okay, if the monster comes in or this particular kind of thing, then we're going to transition between this one theme or this one sound effect or whatever into the next piece, right? Because we talked about music today and sound design is exceptionally complex. It's no longer the case that you can just say media player.play. It's not going to fly in these full-blown games anymore, okay? All right, I think that was the end of that. Yeah, we're done with that. Questions about audio? Hearing none. What did we talk about next? Game designs. I'm going to let you read that. Right, here's some notes that I took for you. There they are. Look at that. There's our review. Okay, let's get into coordinate systems. Okay, in fact, let's just do a high-level overview. We have a couple different coordinate systems, right? What are the coordinate systems that we talked about? Three major ones. Okay, the object space, which is what? Local space. What does that even mean?
The character space.
It's right here in front of you, right? When we make this thing, this monster here, it's going to be made in Blender, Maya, 3ds. It doesn't really matter. That is a local space. Where are the feet of this character? In fact, let me highlight that for you. Right? Very important concept. And what's the thing when you're working with artists in the real world? What do you want to tell them explicitly? Have it centered at 0, 0, 0. Regardless of the animation that they're doing, that creature cannot move unless you explicitly say so. So even the running animation, everything else should be centered at 0, 0, 0. So you've got these sliding feet. Very important to remember that, okay? So that's the local coordinate system. It is the system that the coordinate system that the object was modeled in. What's the next one?
World space.
The world space, which is what?
Level.
It's the level. It's the world that this monster is supposed to be placed in. So if we were to look at it here, in fact, maybe we'll do it from a top-down view. I want to put this character in the world. This is the virtual environment, and I want to position it at whatever position I want to do. So I need a way to go from the local coordinate space to the world space. Yes? Okay. Then we get to camera space. Notice this monster now has a different position. It was 0, 0, 0, and then it went to 6, 19, whatever, and now it is 0, 0, negative 10. What does that even mean? Okay. Everything is from the point of view of the player, right? So we have this camera that's there, and so it's all relative to that. So we need a way to go from local space to world space to camera space, and how do we do that?
Model matrix.
Matrices. How many matrices do we need to get from
2.
here at debate? How many do I need to get from the local coordinate system to the camera system?
2.
7, 12. Yeah. Well, let's talk about that. Right, so how do we get from here to here? We have a model matrix, which does what? Takes us from local space to world space, and then we have a view matrix, which does what? Finishes it out. So we have 2 that take us from all the way through this coordinate system space thing that we've been talking about.
Would there ever be a reason to go back?
I don't think so. There are times when you would want to get out of that and figure out what it is in a different coordinate system. An example of that is shadows, right? So if I have a camera, the way that shadows and textures and all that kind of stuff work is that you have a light, and you actually record what's in the light and what's not in the light, and you have to undo operations. So it's possible to have to undo that at times. It's not an easy thing to do, but it's still possible. Okay, so a lot of times we'll combine these things into one matrix called the model view matrix, but it's best just to keep them separate. Okay, yeah, we talked about that. We'll skip over that. Realize that the order of operations, I think we demoed this in class where we had the dragon, and there's a difference between pushing the dragon out and rotating it and pushing the dragon out. Which one was the way that we did it? What are the order operations to create that dragon, that spinning dragon that we saw in front of the camera? What do you do?
You want to spin it, rotate.
Do I rotate first and then translate, or translate and then rotate? I heard a. We rotate and then translate. Why? Think about the order of operations. I'm going to rotate the dragon a little bit, and then I'm going to push it into the scene, right? And then I take the original model, I rotate it a little bit more, and then I push it into the scene. and then I take the original and I rotate even more, and then I push it into the scene. Versus taking it, pushing it into the scene, and then rotating it. And what am I going to get? An orbiting dragon, right? And I think that was just funny, but it is a very important. When you start seeing really weird things when you do graphics, that's going to be one of them. Okay, here's an example of what we're talking about. If I do the rotation and then the translation, I get that guy. And if I do the opposite, then I get that guy. Look through the slides. I think you'll appreciate them. Look at that humor there, too. I've got a little frowny face. It's just funny. Laughs galore. Yeah, see? I told you. Okay, so the last one that we talked about is the projection matrix. We have two different kinds of projection matrices. What are they? Orthographic and perspective. What's the difference? It looks like, oh, it doesn't look like. I thought we had a picture of that. Maybe it was in the graphics one. Let's get to the graphics one. We have 9 minutes and I must finish. Here we go. We'll come back to it. In fact, it's going to be in the next, here, let's finish that part. Okay, here you go. This is what it looks like. Perspective has what? Depth. Okay, so that last component that we talked about, why there's a 4x4, is to get these kinds of effects. Okay, so these are all orthographic, this upper left, and lower right. You can see that everything's flattened out. Architects use that all the time, versus what we want to really see is the view that we would normally see that would have depth is in the upper right. Okay, let's go back up. Major phases of the graphics pipeline are what? You can read them to me if you wish.
Vertex processing.
Okay, the first one is the vertex processing, which does what? Don't say process the vertex.
Creates a cloud of vertices.
It creates a cloud of vertices, right? So what it's really done is it's created the rotated, translated, scaled version of the vertices. Okay, so basically we've taken all of these things and then we've positioned all of the vertices correctly in the environment, let's say. The next one is the clipping and primitive assembly. What's the primitive assembly mean? Builds the triangles, right? So remember, we've got a point cloud that's over there, and then we have to connect all of the triangles together. And then the clipping is an easy one. What is that? If it's not viewable, then you throw it out. Okay. Rasterization, you have no control over this, but rasterization means this doesn't help at all. I know. It's like this, right? You did that before. Rasterization is when you're putting the pixels onto the screen. What's really going on is determining which pixels are even relevant. Which ones are the background color and which ones are actually relevant. And then fragment processing is where you assign those things a color. Okay, we talked about coordinate systems. Talked about that. Let's skip that. Have a couple of different buffers. Why is the depth buffer so important? What is the depth buffer? Not necessarily.
Which one's strong?
Okay, remember we have several different things that are going to fit on the screen, and we need to figure out which one is in the front. So what's going to happen, all of these little pixels are going to be displayed, and whatever pixel is the closest after that perspective division, by the way, what's going to happen? It's going to be the one that wins. Okay, so we don't have to do any sorting. We basically just say if this pixel is closer than one of the other pixels, then draw that pixel, discard the other one. Yes?
And isn't there an issue with that, with like alpha blending?
Yeah, when you get into alpha blending, never mind. We're moving on. Aliasing is bad. Okay. And what do we want to do? Use anti-aliasing. There we go. Okay, wireframe, we're cool with that. Okay, 2 terms. Hidden surface removal versus back face culling. Very important. What is hidden surface removal?
Takes away stuff that hides it.
It hides stuff that should not be seen. If it's back behind something else, hidden surface removal says that objects that are further away, that are occluded by objects that are closer, shouldn't be visible. How do we do that?
Ray casting.
No ray casting. We just talked about it. The depth buffer. That's what the depth buffer does, right? Does hidden surface removal for us. Okay? Versus back face culling, which is any triangles facing away from the camera are not rendered. Why do we even care about that? Saves time. It actually cuts it generally in half, and so it is a big deal when you're working in these things like OpenGL to turn on backface culling. Okay, it's going to speed things way, way up. There's an example of a screw up in a game. All right, solid shading, skip it. Flat shading, don't care. Texture mapping is important. What is it? What is a texture? It's a picture, right? So we're putting that on the geometry. Why do we do that?
Cool.
It makes it look better, yes. Okay. Graphic organization. Characters. We know that if we want to have animated characters, what do you have to do? You have to have a skeleton here. What does a skeleton do? It tells where to move all of the vertices, right? So some may move in different directions, but that's how that's generally done. You should take a class in Maya 4113. I think a lot of you might have to take. All right. Skip over BSPs and all that kind of stuff. We didn't really get into that. You know what? We didn't talk about any of this, so I'm not going to. We'll come back to that. We're going to come back to all of that stuff. So stop where we just were. Okay. I'm not going to finish that lecture. I think that would be unfair. Yes.
Are you going to talk about double buffering?
What is double buffering? That's a fair question. Yes.
It's having an entire frame on a drawing at the time.
Remember, with double buffering, we have an off-screen thing that we're drawing to, right? Why do we have to do that? Because the human eye is fast enough to actually see the drawing. And so we fill out this whole frame right here. We have it ready to go. And then what do?
Switch on and off.
We switch what the user's looking. Now we're looking at this thing over here. Now we're going to look at the thing that we just drew. And then what happens? We start drawing the next frame, the future frame, over here. And once we fill it in, we tell the user, okay, now you need to look at this buffer over here, right? Why do we use that? It eliminates all of this frame tearing and all of this flickering and all these effects that you would see if you didn't do that. Yes?
Is it really the future frame, or is it what's actually the frame?
It does not matter. It is the next frame in the series, whether it's in the future or not, or a current. It depends on, are you looking in the past? Actually, you are looking in the past right now. I want you to appreciate this. Think about it. You're seeing me in the past right now because it takes time. And he's leaving right now. He's like, the heck with this. It's too
I don't need this.
All right, so test has, I think, 5, 6 questions somewhere on there. It's going to be a lot of descriptions of concepts. I'm assuming you know how to do programming. There's no XNA, no Unity, nothing like that that's on there. It's mostly a conceptual exam, okay? When will we have Bezier curves? I was at the game jam this weekend, so I didn't get to grade them. But I will get to those probably tomorrow. Okay.
I was good, looking up, I had to put my coat on.
Sure, that's what they all say. All your criminals are like.